Depending on your language, you may be familiar with the term heap as meaning an area of memory where you allocate objects, but that's not what we're talking about here. A heap is a specific data structure we can use for our own purposes. They're often used in sorting algorithms. You may have even heard of something called a heap sort. But they're also a way of implementing other abstract data types, like the priority queue we discussed earlier in the course. Heaps are usually implemented as a binary tree, not a binary search tree, but still a binary tree, a collection of parent-child nodes with a maximum of 2 children under any one parent. But there's a different, simple rule that we use to give a heap a totally different internal structure to a binary search tree. So the basics. Heaps are a collection of objects. As we add items to this heap, they are always added top to bottom, left to right. We completely fill out any level before moving on to the next, so we don't have to worry about the tree becoming unbalanced like a binary search tree can. But it's not just random things added in any random order. There is a rule we apply when we're doing this. And to apply this rule, we have to answer one question. Do we want our heap to be a min heap or a max heap? What that means is, do we want the top of the heap, our root node, to always contain the lowest value in the entire heap? Or do we want the top of the heap, the root node, to always contain the highest value in the entire heap? If we say we want a min heap, the lowest value at the top, then the one rule applied is that any child node must be greater than its parent node. If we say we want a max heap, the highest value at the top, any child node must be less than its parent. And that simple rule will do it. Let's see a min heap in action. So, the root node is created. I'm going to go again with an integer value of 50. We add another node. This will be 100. Now, remembering that heaps always add top to bottom, left to right, so it's ready for something to be added just at that left child node position. And we check, is this allowed? Well, with a min heap, this child must be more than parent, so 100 is more than 50. We're good. We'll just slot it in there. The next open position will be the right child of the root node. We create a new node. It's 75. We'll check that. Is the child node more than the parent? Yes, it is. Not a problem. Now notice we don't care if this value 75 is less than or greater than its sibling. That doesn't matter at all, just that it's more than its parent. So we continue top to bottom. Well, it's a binary tree. We can only have 2 children, so the next available slot is going to be the left child of that 100 node. We need to go this one level deeper. We add this new node. It's 150. It checks to see if it is greater than its parent node, and there's no problem there. We then add a node called 99. Well, the available slot is the right child of that 100 node, so it'll dump it in there, and then it does the little check. Is 99 more than its parent? Well, no, it isn't, so it's going to swap those. Then it's going to check before finishing, well, is 99 more than its parent? And yes, it is. That one's absolutely fine. And this little swapping of nodes is how a heap keeps itself organized. Then let's add the number 76. The only available slot now is the left child of 75. Again, we're going top to bottom, left to right. So it'll slot it in there. It'll compare it to the parent. It's more than the parent. Not a problem. We're fine. Then we'll add the number 49. The available position is the right child of 75. We'll put it in there. We will compare that to its parent. Is 49 more than 75? No, it isn't. So we need to swap those two. And before it's done here, because we move things around, it's also going to compare 49 to its parent. And no, it isn't more than that, so we need to swap those two. We're actually swapping the root node. And this is the way that with a min heap, we always bubble up the lowest value to the very top of the heap, to the root. A max heap is exactly the opposite, that a child must be less than its parent, so we always bubble the highest value up at the top. But it is important to understand that a heap is not a fully sorted data structure. Unlike a binary search tree, which does stay sorted and where we can easily traverse the tree and get everything out in sequence, that does not work with a heap. Because if you notice at any particular level past the root, the values do not have to be in any specific order, just as long as they're all more than their parent. One of the benefits of this is a heap does not have to do as much reorganization of itself as may be necessary with a binary search tree. The one thing we can be sure about is that the minimum or the maximum value will always be at the top. It's because of this, one thing heaps are most useful for is the idea of a priority queue, which we covered conceptually earlier on, where we don't care that much about the order of most of the objects. Whatever order we've added them is fine, unless something should be considered a high priority, in which case we could give it a low value and see it bubble up to the top. So, over to the language support. We have pretty good support for heaps across the various languages. In Python, there's the heap queue. This is Python implementing their priority queue as a min heap. If you notice it, what they call it is binary trees for which every parent node has a value less than or equal to any of its children. That's exactly what we just went through. There's no built-in heap in Ruby, and as far as I'm aware, there isn't one in .NET either. Over in Objective-C, there is the CF binary heap, which they even mention in the overview. Binary heaps can be useful as priority queues. It's one of the things they're really good at. Java also has a priority queue, which, as you see here, is based on a priority heap. It's doing exactly what we've just gone through here. Other than that, C++ has priority underscore queue container that's also implemented as a heap. And that's heaps. It may not be a wonderfully general-purpose data structure, but for things like priority queues, it's the best possible choice.